NASA's James Webb Space Telescope, when humanity gazes into the night sky, though much of Webb's fame comes from its breathtaking images of galaxies, nebulae, and exoplanets, it is also reshaping our view of the solar system. And it was Webb's unmatched sensitivity that revealed a new, faint moon orbiting Uranus, proving that even the quietest corners of our cosmic neighborhood still hold secrets. The story of Webb began long before its launch. In the 1990s, as the Hubble Space Telescope dazzled the world with its stunning images, astronomers dreamed of what might come next. Hubble had shown us galaxies billions of light years away, the death of stars, and the intricate details of our solar system, but it was limited. Hubble could not see far enough into the infrared spectrum, where the faint heat signatures of the earliest galaxies and the hidden structures of nearby planets resided. Thus was born the idea of a next-generation space telescope. The goal was bold: to peer deeper into the universe than ever before, to capture the faint glow of the first galaxies after the Big Bang, and to study the atmospheres of planets around other stars. But such an instrument would have to be revolutionary, not just an upgrade. It would need to be larger, colder, sharper, and smarter than anything that had come before. Designing Webb was a challenge that stretched the limits of engineering. Its most iconic feature is its primary mirror, a golden hexagonal array measuring 6.5 meters, 21 feet, across nearly 3 times the size of Hubble's mirror. Because it was too large to fit into a rocket fairing, the mirror had to be designed to fold up like origami and then carefully unfold in space. Each of its 18 hexagonal segments is coated with a thin layer of gold to optimize reflection in infrared light. But the mirror was only part of the puzzle. Any warmth from the telescope itself would drown out the delicate heat signatures of distant objects. Engineers solved this with the sun shield, a tennis court-sized, 5-layer membrane of Kapton that blocks sunlight and radiates heat away. On one side of the shield, temperatures can reach nearly 100 degrees Celsius, 212 degrees Fahrenheit, while on the other, where the instruments sit, it plunges to minus 233 degrees Celsius, minus 388 degrees Fahrenheit. This staggering temperature difference is what allows Webb to function as the most sensitive infrared observatory ever built. After decades of planning, construction, delays, and rising costs, over the next month, it performed a flawless ballet of deployments, unfolding its sunshield, extending its mirror, and aligning its instruments. By January 2022, it had reached its home, the second Lagrange point L2, a gravitationally stable spot 1.5 million kilometers from Earth. From there, Webb began its mission to look both far into the universe and close within our solar system. At the heart of Webb are its 4 primary instruments: NIRCam, near-infrared camera, Webb's primary imaging tool, capable of capturing faint galaxies billions of light-years away. It is also key to studying planets, moons, and rings in our own solar system, where infrared light reveals hidden structures in visible and invisible wavelengths. NIRSpec, near-infrared spectrograph. This instrument breaks light into its component wavelengths. With NIRSpec, astronomers can detect water vapor, methane, carbon dioxide, and other molecules. MIR mid-infrared instrument. Operating at longer infrared wavelengths, it is especially useful for studying planetary systems and the thermal emissions of small. FGS NIRIS fine guidance sensor, near-infrared imager, and slitless spectrograph. The FGS keeps Webb precisely pointed, while NIRIS aids in exoplanet studies and faint object imaging. They allow it to see objects 100 times fainter than what Hubble could detect, and to resolve details with clarity never before possible in the infrared. Infrared light is key to Webb's power. Infrared can penetrate dust clouds that obscure stars and galaxies. It reveals the heat signatures of cold objects like planets, asteroids, and moons. It allows astronomers to look back in time. Closer to home, infrared is essential for studying the outer solar system. Distant planets like Uranus and Neptune reflect little sunlight, making them dim, invisible light. Their small moons are even fainter. But in the infrared, Webb can detect their subtle glow, distinguishing them from the background stars. This is how it managed to find a previously unknown moon orbiting Uranus, something invisible to less sensitive telescopes. Webb in the solar system, though designed primarily for deep space astronomy, Webb is proving to be a powerful tool for planetary science. Already it has observed Neptune's rings in astonishing clarity, showing details not seen since Voyager 2, Saturn's atmosphere, revealing unexpected thermal structures, Jupiter, capturing auroras and delicate details of its atmosphere, distant asteroids and comets, providing clues about the early solar system. For Uranus, Webb has already delivered unprecedented images. In early 2023, it captured the planet with remarkable clarity, showing 11 of its 13 known rings and several of its larger moons glowing faintly in infrared light. These observations hinted that Webb could uncover even more hidden features around the ice giant. And then came the discovery: a new, faint moon orbiting Uranus, likely only a few kilometers wide. Such a small object reflects almost no sunlight, making it invisible in most telescopes. But Webb's sharp infrared vision caught it, distinguishing its subtle motion against the backdrop of distant stars. The find demonstrates Webb's unmatched ability to probe the faintest, coldest, and most elusive objects in our solar system. A cosmic detective, what makes Webb extraordinary is not only its ability to capture beautiful images, but its power to act as a scientific detective. When Webb observes Uranus, it is not just taking pictures. It is measuring brightness across wavelengths, analyzing chemical signatures, and tracking motions over time. This is how astronomers confirmed that the faint they saw was not a background star but a new moon bound to Uranus by gravity. In this sense, Webb is not simply an observatory, but a multi-tool of discovery. It can image, analyze, and compare objects in ways no previous telescope could. For planetary scientists, it is like lifting a veil, revealing structures and companions that were always there but too faint to see. Webb's challenges and triumphs. The journey to Webb's success was far from easy. The telescope faced over 2 decades of development, multiple redesigns, and a ballooning budget that eventually exceeded $10 billion. Critics questioned whether it would ever launch. But the success of its deployment and the flood of discoveries since has silenced most doubts. Today, Webb stands as a triumph of international collaboration, involving NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA. Its discoveries belong not to one nation, but to humanity as a whole. The fact that it has already discovered a new moon around Uranus, an unexpected bonus to its mission, demonstrates just how transformative this observatory is. Webb is not only answering old questions, but also asking new ones, pushing astronomers to rethink what is possible. The solar system through new eyes. For centuries, telescopes have steadily improved, each new generation pushing deeper into the universe. Galileo's small refractor revealed the moons of Jupiter. Herschel's handmade reflector unveiled Uranus. Hubble showed us galaxies at the edge of time, and Webb carries this legacy forward, extending our vision into the infrared frontier. Through Webb's eyes, Uranus is no longer just a bland blue orb at the edge of the sun's light. It is a dynamic world, surrounded by rings, moons, and now, thanks to Webb, a newly discovered companion. The telescope reminds us that the solar system is still alive with mystery, waiting for the right tools to reveal its hidden wonders. The promise of more discoveries. The new moon around Uranus is almost certainly not the last. Webb's mission is planned for at least a decade, and during that time, it will continue to survey the ice giants, rings, and distant Kuiper Belt objects. Each observation has the potential to uncover more faint moons, more structures, and more clues about how the solar system formed. In a way, Webb has brought us full circle. Just as William Herschel expanded the solar system with his telescope in 1781, Webb is expanding it again, showing that even centuries later, Uranus still has surprises left to share. And perhaps the most exciting part, this is only the beginning.